Welcome to High Physics channel. In today's video, we are going to discuss about numerical problems on photoelectric effect. Last video, we have seen the theory, and today we are going to see the numerical part. For example, the first problem reads like this. Monochromatic light of frequency 6 Hz. Frequency is given as 6 into 10 power 14 Hz produced by a laser. The power emitted is 2 into 10 power minus 3 watt, that is 2 milliwatt. Estimate the number of photons emitted per second on an average by the source. This is the question. Frequency is given, power emitted is given, and we have to find out the number of photons emitted per second, that is n we have to determine. So we know that the power P is nothing but energy per unit time. So that is E by T. Here, as we see here, given in red, power P is equal to E by T. Right? E can be written as N into h nu, where h nu is the energy of a single photon. And suppose there are n photons that are incident, then we can write it as N h nu as the incident energy divided by T. Right? This entire quantity is given as 2 into 10 power minus 3 watts. Right? So this is what it is given. And we have to find out this n per second, that is T can be considered as 1 second. Right? Now we have to calculate the n. Right? How to calculate n? N is, from this formula we can calculate n is equal to P into T. We take this T to the other side of the equal to symbol. So P into T divided by h nu is going to be our n. Right? So T is 1 second multiplied by 1. P is given already, 2 into 10 power minus 3 watt divided by h nu. Right? What is h? H is the Planck's constant. It is a constant given by this value 6.6 into 10 power minus 34 multiplied by nu. Nu is given here 6 into 10 power 14 Hertz. 6 into 10 power 14 Hertz is the frequency. Therefore, we calculate this. We have to, this is the numerator, and we multiply this entire this together and get a denominator, and now divide the numerator by the denominator. We get this answer 5.05 into 10 to power 15 number of electrons are emitted per second. Right? This is what our calculation reads. So P is equal to E by T, E is equal to NH nu. From that we are going to calculate N. It's as simple as that. And the second part of this problem reads as, draw a plot showing the variation of the photoelectric current versus intensity. This is a straightforward question, as we have seen in the previous video while discussing the photoelectric effect theory. Therefore, in the x-axis we are going to take the intensity of the incident radiation, and in the y-axis we are going to take the photocurrent, right? And this is going to be directly proportional, right? Linear. So we are going to get a linear curve. So this is as simple as that. Shall we move on to the second part? The second question. This second numerical problem reads like this. Ultraviolet light of wavelength 2271 angstrom unit from a 100 watt mercury source is incident on a photocell made up of molybdenum metal. If the stopping potential is 1.3 volts, estimate the work function of the metal. So wavelength is given, right? Power is given, right? And stopping potential 1.3 volt is given. Stopping potential is given, right? And what is asked? Asked is stopping potential. I mean work function. Work function is 5 naught, right? So we know Einstein's photoelectric equation, which reads as K max is equal to h nu minus 5 naught. Right? K max, kinetic and maximum kinetic energy, can be written like this. H nu is the quantum energy of the each chunk that is incident minus the work function of the metal. Right? And this Kmax can also be written in terms of the stopping potential as E into V naught, where V naught is the stopping potential, right? Stopping potential is given here. Therefore, combining these two equations, the first and the second equation, we can write, instead of this Kmax, we can write E V naught. So E V naught is equal to H nu minus phi naught. From this we can calculate phi naught. We take this phi naught to the other side and we move this E V naught to this side. Therefore, phi naught is equal to H nu minus E V naught is going to be our formula to calculate the work function, right? Nu is not given. Instead of nu, they have given the wavelength, right? So we know the relation between the nu and lambda. So H is C by lambda. Nu is equal to C by lambda. Therefore, instead of nu, we are going to substitute C by lambda. Therefore, it becomes H C by lambda. H nu can be written like this: H into C by lambda minus E V naught. So we substitute here. H is 6.6 into 10 power minus 34. C 3 into 10 power, C is the velocity of the light, 3 into 10 power 8 meters per second, and the wavelength is given here, 2271 angstrom unit, which we converted into meter. 2271 into 10 power minus 10 meters, right? Angstrom to meters, 10 power minus 10 meters, minus E, charge of an electron, we know that 1.6 into 10 power minus 19 joules, into this V potential is given here, 1.3 volts. So straightforward substitution. We simplify this, we get phi naught is equal to 6.64 in 10 power minus 19 joules. We want to be converted into electron volt. So how to convert this? We divide this number 6.64 joules by 1.6 in 10 power minus 19. We get 4.15 electron volt. So joules divided by 1.6 in 10 power minus 19 is going to give you the value in electron volt, right? So this is 4.15 electron volt. This H nu value will be around 8.76 or something. If you calculate, we can get it, right? This value. If you simplify this H C by lambda, this part, first part, right? And the phi naught is 4.15 electron volt. Therefore, this H nu is greater than this phi naught. As a result, the photoelectric emission will take place, right? Photoelectric emission will take place because H nu is greater than phi naught. If it is less than phi naught, then photoelectric emission will not take place, right? This we have seen in our theory. And the second part says, how would the photocell respond to high intensity, say 10 power 5 watt per meter square red light of wavelength 6328 angstrom unit produced by helium laser. So we have to substitute, instead of 2271 angstrom unit, it has been given 6328 red light, 6328 angstrom unit. So instead of this 2271, we substitute 6328, right, into 10 power minus 10 meters in meters, right? And in the first problem, we got H nu as 8.76, right? But here what we are getting, 1.96 electron volt. So phi naught is 4.15 electron volt. Definitely in this case itself 4.15 electron volt. Now if you substitute this, you have to do the calculation, right? 6328, you substitute instead of 6328 and find out this. This is going to be more than this value, and therefore 1.96 is our H nu. Therefore H nu is less than this phi naught work function. Therefore photoelectric emission will not take place. You can substitute. Merely you substitute this to, instead of 2271, you substitute 6328 and calculate this, right? H nu I have calculated and given, right? Hc by lambda, that is 1.96 electron volt. Therefore it is going to be less than this. As a result, no photoelectric emission is going to take place. So Einstein's photoelectric equation, from Einstein's photoelectric equation and from kinetic energy equation, which is given by E V naught, stopping potential, E into V naught. E is the charge of the electron, V naught is the stopping potential. From there we can calculate this phi naught, which is the work function of the metal, right? And one more third problem is a light source of wavelength 520 nanometer emits 1.04 into 10 power 15 photons per second, right? N is given here, wavelength is given, while the second source of wavelength 460 nanometer produces 1.38 into 10 power 15 photons per second. Then we have to find out the ratio of the power, right? Ratio of the power between the second source and the first source, right? First we calculate the first one. So P, let the power of the first source be P, that is equal to E by T as we have calculated in our first problem. Then NH nu by T, that is equal to nu, instead of nu we are going to substitute C by lambda, because lambda is given, nu is not given. Therefore NHC by lambda T is going to be our equation, right? And that is equal to, N is here given 1.04, as we are going to substitute. N is given in the problem 1.04 into 10 power 15, right? It is not in 15, 10 power 15, it is 10 power 15, okay? 15 photons, 1.04 into 10 power 15, so it is not 1015, right? 10 power 15 into H 6.6 into 10 power minus 34, C is as usual 3 into 10 power 8 meters per second, and divided by lambda value is 520 nanometers, 520 into 10 power minus 9 per second is asked. So T is 1 second, we substitute, instead of T we substitute 1. Therefore what we get 3.96 into 10 power minus 4. This is P, first source. Similarly we apply for the second source. Second source, we change the wavelength, we change the N, that's all. So we change the N as 1.38 into 10 power 15, right? We change the wavelength, instead of 520 we are going to substitute 460 nanometers, 460 in 10 power minus 9 meters. What we are going to get, we are going to get, I slowly remove this so that you can get 5.94 into 10 power minus 4. What is asked? The ratio of the second power to the first power. So second power is P dash divided by P is going to be our answer. P dash divided by P, 5.94 in 10 power minus 4 divided by 3.96 in 10 power minus 4, we are going to get 1.5. So we have covered 3 numerical problems, 3 important numerical problems in photoelectric effect. Thank you.